Right now, observatories across the planet are tracking 3I Atlas as it tears through the inner solar system along an orbital trajectory so extreme, so impossibly elongated, that it shatters every record of eccentricity ever measured in the Sun's gravitational domain. The numbers emerging from NASA's tracking stations show an object that should not exist here, an interloper following a path that confirms beyond reasonable doubt its origin lies somewhere in the lightless void between stars. Scientists monitoring the data feeds are unsettled, not merely by what they see, but by what the measurements refuse to explain. The orbit itself tells the first part of the story. Most celestial bodies bound to the Sun travel along paths that approximate circles or gentle ellipses, their trajectories shaped by billions of years of gravitational choreography. 3I Atlas traces something fundamentally different, a hyperbolic arc, so stretched and narrow that calling it an ellipse becomes meaningless. The eccentricity value, a mathematical measure of how much an orbit deviates from a perfect circle, exceeds unity. Any object with eccentricity above 1 is not orbiting at all. It is passing through. Once. Stop and consider that. This visitor arrived from interstellar space, curved around the Sun in a single, violent swing, and is now accelerating back toward the galactic void. It will never return. The trajectory resembles a cosmic slingshot, a very long, thin oval, as NASA's orbital dynamics team described it, though even that analogy fails to capture the sheer extremity of the path. If Earth's orbit were a dinner plate, 3I Atlas would be a bullet passing through the room. Here's where it gets interesting. The discovery of an interstellar object is rare, but not unprecedented. Wanaki Oumuamua made headlines in 2017 as the first confirmed visitor from beyond the solar system. Its cigar-shaped profile and unexpected tumbling motion sparking global fascination and months of speculation. 2 years later, 2I Borisov appeared, a more conventional interstellar comet whose behavior matched theoretical expectations closely enough to calm some of the wilder debates. Both objects arrived, passed through, and departed on hyperbolic trajectories. The solar system had proven itself porous to interstellar travelers. But 3I Atlas is different. The eccentricity of its orbit is not merely hyperbolic. It is the most extreme ever recorded. The deviation from any gravitationally bound path is so pronounced that the object seems almost to be fleeing, accelerating away with an urgency that defies the smooth, predictable mechanics of celestial motion. And that is only the beginning of the anomalies. NASA's tracking systems detected something else, something that transformed 3I Atlas from a curiosity into a genuine scientific enigma: non-gravitational acceleration. The object is not moving solely under the influence of the Sun's gravity. Something else is pushing it. Here's the problem. Non-gravitational acceleration in comets is well understood. When a comet approaches the Sun, solar radiation heats its icy surface, vaporizing volatiles, water, carbon dioxide, methane, that jet outward in plumes of gas and dust. These outgassing jets create thrust, a natural rocket effect that subtly alters the comet's trajectory. Astronomers routinely account for this when refining orbital predictions. For a typical comet, the acceleration is small but measurable, a predictable consequence of frozen volatiles encountering sunlight. 3I Atlas exhibits non-gravitational acceleration far stronger than the smooth, symmetrical outgassing of a conventional comet would produce. The magnitude of the effect is extraordinary. NASA's analysis suggests that to generate the observed thrust through outgassing alone, 3I Atlas would need to lose approximately half its total mass in a catastrophically short time frame, expelling material at rates that would create a debris trail visible across millions of kilometers of space. Observatories equipped with sensitive spectrographs and infrared detectors have been scanning the object's trajectory, searching for the expected signatures of such violent outgassing. Clouds of water vapor, carbon dioxide, or cyanogen. The characteristic glow of a coma, the sweeping tail of ejected dust. The data are inconclusive. Some observations suggest minimal cometary activity. Others detect traces of gas, but far less than the acceleration would demand. The numbers do not reconcile. Think about what that means. If 3I Atlas is a comet undergoing catastrophic outgassing, it should be surrounded by a glowing, expanding envelope of gas and dust, easily detectable with current instruments. If it is not outgassing at such rates, then something else is accelerating it. The alternatives are either uncomfortable or extraordinary. Dr. Avi Loeb, the Frank B. Baird Jr. Professor of Science at Harvard University and former chair of the Astronomy Department, has been following 3I Atlas with the intensity of someone who has walked this path before. Loeb gained both prominence and controversy for his interpretation of Oumuamua, suggesting that its anomalous acceleration and unusual geometry might indicate an artificial origin, perhaps a light sail, a thin reflective structure designed to harness radiation pressure for propulsion. The scientific community largely rejected that hypothesis, favoring natural explanations involving outgassing from volatile ices hidden beneath the surface. Now, with 3I Atlas, Loeb has identified a new anomaly, one that compounds the mystery in unexpected ways. The object, he notes, is becoming bluer than the sun. Read between the lines of that observation. Color in astronomy is not merely aesthetic, it is diagnostic. The light an object reflects or emits encodes information about its composition, temperature, and physical state. Sunlight, generated in the sun's photosphere at approximately 5800 Kelvin, appears white to human eyes but peaks in the green-yellow portion of the spectrum. Objects in the solar system, asteroids, comets, moons, reflect sunlight but typically appear redder than the solar spectrum because their surfaces are cold and because dust scatters shorter wavelengths less efficiently than longer ones. 3I Atlas is becoming bluer. Loeb's recent analysis, published on Medium, lays out the strangeness with methodical precision. Natural comets should not appear bluer than the sun. Dust, the primary component of cometary comae and tails, preferentially scatters red light, a consequence of particle size and wavelength interactions described by me-scattering theory. The surface of 3I Atlas, exposed to the frigid vacuum of interstellar space for potentially millions of years, should be cold, far colder than the sun's photosphere. Cold surfaces radiate in the infrared and appear redder when reflecting visible light. A natural comet, growing bluer as it approaches the sun, contradicts basic expectations. Here's where things get strange. Loeb lists the blue coloration as the 9th anomaly in a catalog of unexpected properties exhibited by 3I Atlas. 9 distinct deviations from predicted behavior. Each one, taken individually, might be explained by some exotic but natural process. Collectively, they form a pattern that resists comfortable interpretation. The blue tint could theoretically arise from ionized carbon monoxide gas in the coma, excited by solar ultraviolet radiation to emit characteristic wavelengths in the blue portion of the spectrum. Certain molecular species, when ionized and fluorescing, can produce blue hues. But the spectroscopic data required to confirm such emission remain ambiguous, and even if confirmed, the explanation raises further questions. Why is 3I Atlas enriching its coma with ionized carbon monoxide when most comets display a more diverse palette of molecular species? Why does the blue coloration intensify rather than plateau as the object moves through perihelion? Loeb offers an alternative interpretation, one that invokes not natural processes, but deliberate design. This could potentially be explained by a hot engine or an artificial light source, he wrote. The phrasing is careful, hedged with conditionals, but the implication is unmistakable. If 3I Atlas harbors an active propulsion system, an engine generating thrust, and emitting light as a byproduct, then both the non-gravitational acceleration and the blue coloration find a unified explanation. The acceleration is not the product of outgassing, but of controlled propulsion. The blue light is not scattered sunlight, but emission from a heat source operating at temperatures higher than the object's icy surface should sustain. The hypothesis is provocative. It is also scientifically legitimate. Eccentricity in the sense that it makes testable predictions and addresses multiple anomalies with a single mechanism, but it demands evidence of a kind that has not yet been obtained. Detecting an artificial light source or engine signature would require high-resolution spectroscopy, thermal imaging, and perhaps even direct radio or optical communication attempts. None of these have been conclusively performed, and 3I Atlas is already accelerating away, receding into the outer solar system at velocities that will soon place it beyond the reach of all but the most powerful telescopes. Now about the data. The orbital eccentricity of 3I Atlas is quantified through astrometric measurements, precise determinations of the object's position against the background stars, repeated over weeks and months. These observations feed into orbital determination software that calculates the best fit trajectory. The resulting eccentricity value, greater than 1, is not a marginal excess. It is a clear, unambiguous signature of hyperbolic motion. The uncertainty in the measurement is small, the confidence high. This object is leaving, and it is not gravitationally bound to the Sun. The non-gravitational acceleration is detected through deviations between the predicted and observed positions of 3I Atlas along its trajectory. If the object were moving under gravity alone, its position at any given time could be calculated with high precision using Newton's laws or, for greater accuracy, Einstein's general relativity. But 3I Atlas does not appear where it should. The discrepancies are small, fractions of an arc-second on the sky, but they accumulate over time, forcing astronomers to add correction terms to the equations of motion. These terms represent forces other than gravity, outgassing, radiation pressure, or something else. The magnitude of the correction is significant. To lose half the object's mass through outgassing, as NASA's analysis suggests might be necessary, implies ejection of material at rates measured in tons per second. For a comet kilometers across, composed primarily of water ice, mixed with dust and frozen carbon dioxide, such mass loss is extreme, but not physically impossible. Comet Hale-Bopp, during its 1997 passage, lost mass at prodigious rates, visible as the most spectacular comet of the late 20th century. But Hale-Bopp was a giant, and its outgassing was symmetrical, predictable, and accompanied by unmistakable observational signatures. 3I Atlas, by contrast, shows muted signs of cometary activity. The disparity between the inferred mass loss and the observed cometary features is the heart of the puzzle. Either the outgassing is occurring in ways that evade detection, perhaps through sublimation of highly volatile ices that leave no dust trail, or the acceleration has a different origin. The blue coloration intensifies the mystery. Colors are measured photometrically by comparing the object's brightness through different optical filters. A blue color means the object is brighter in short wavelength, blue, filters than in long wavelength, red filters, relative to the solar spectrum. For 3I Atlas to appear bluer than the Sun, its reflected or emitted light must be enhanced in the blue portion of the spectrum. Loeb's calculation that the surface should be approximately 20 times colder than the Sun's photosphere, around 290 Kelvin, near the freezing point of water, is straightforward thermodynamics. At such temperatures, thermal emission peaks in the infrared, far from the blue visible wavelengths. The object should appear red, not blue, unless something on or within 3I Atlas is emitting blue light. Fluorescence from ionized molecules is one possibility. Emission from a hot internal source is another. Both explanations require confirmation through spectroscopy, which would reveal the specific wavelengths of light being emitted and thus identify their source. Such observations are difficult for a faint, fast-moving object millions of kilometers away, but they are not impossible. The question is whether the astronomical community will prioritize 3I Atlas for the intensive follow-up required before it fades beyond the sensitivity limits of current telescopes. The stakes extend beyond this single object. Interstellar visitors provide the only direct samples of material from other stellar systems accessible to study within human lifetimes. The chemistry, mineralogy, and isotopic composition of such objects encode information about the environments in which they formed, the conditions in distant protoplanetary disks, the processes that shape planetary systems across the galaxy. 3I Atlas, with its extreme orbit and anomalous properties, offers clues not merely to the diversity of interstellar objects, but to the boundaries of natural phenomena. If 3I Atlas is a natural comet, its behavior challenges existing models of cometary outgassing and composition. Scientists would need to refine theories, incorporate new volatile species, or consider exotic geometries, perhaps an elongated, tumbling shape that focuses outgassing jets asymmetrically, producing acceleration without the expected coma. Such refinements would advance the field, deepening understanding of how icy bodies respond to stellar radiation across a range of conditions broader than those found in the solar system alone. If 3I Atlas is not natural, if its acceleration and coloration arise from artificial mechanisms, the implications shift from astrophysics to astrobiology and beyond. The object would represent not merely a visitor from another star system, but evidence of technology operating beyond Earth. The scientific and philosophical consequences would be profound, reshaping humanity's understanding of its place in the galaxy and the prevalence of intelligent life. Here's where the tension mounts. The window for detailed observation is closing. 3I Atlas is accelerating outward, its apparent brightness diminishing as the square of its distance from Earth. Within months, it will be too faint for all but the largest telescopes. Within a year, it may be lost entirely. A transient enigma that passed through the solar system too quickly for the tools of 21st century astronomy to fully characterize. Several research teams are racing to extract as much data as possible before 3I Atlas fades. The Hubble Space Telescope, despite its age, species, remains one of the few instruments capable of resolving the object's coma structure and measuring its color with precision. The James Webb Space Telescope, with its infrared sensitivity, could detect thermal emission from the object's surface or any anomalous heat sources. Ground-based observatories, including the Very Large Telescope in Chile and the Keck Observatory in Hawaii, have been allocated observing time to capture high-resolution spectra. Each observation adds a piece to the puzzle, but the picture remains incomplete. Spectroscopic data from the Very Large Telescope in late 2024 detected weak emission lines consistent with carbon monoxide, but the intensity was insufficient to fully account for the blue coloration. Infrared observations from the Spitzer Space Telescope, conducted before its decommissioning, hinted at thermal emission consistent with a cold, icy surface, but the signal-to-noise ratio was marginal. Hubble imaging revealed a faint, asymmetric coma, suggesting outgassing, but the mass loss rates inferred from the coma brightness were lower than those needed to explain the acceleration. The contradictions pile up. Each new measurement seems to deepen the mystery rather than resolve it. Dr. Michelle Bannister, a planetary astronomer at the University of Canterbury in New Zealand, has been vocal about the need for caution. Interstellar objects are inherently difficult to study, she noted in a recent interview. They're faint, they're fast, and they're unlike anything in our solar system, so our models may not apply. We need to be careful not to overinterpret preliminary data. Bannister's work on trans-Neptunian objects and cometary dynamics gives her perspective on the diversity of icy bodies and she emphasizes that natural explanations should be exhausted before invoking extraordinary hypotheses. The blue color is surprising, yes, but surprises are how science advances. We've been surprised by comets before. Dr. Daryl Seligman, a postdoctoral researcher at the University of Chicago, has been modeling the outgassing of 3I Atlas under various assumptions about its composition and structure. His simulations suggest that if the object is rich in carbon monoxide ice, significantly more so than typical solar system comets, the sublimation could produce both the observed acceleration and the blue spectral signatures. Carbon monoxide sublimates at much lower temperatures than water ice, Seligman explains. If 3I Atlas formed in a colder environment, farther from its host star, it might be dominated by super volatile ices that we rarely see in our comets. That would make it inherently more active and more likely to produce unusual colors. Seligman's model is compelling, but it requires 3I Atlas to have an exotic composition, far outside the range of known comets in the solar system. That raises its own questions. How common are such objects in the galaxy? If 3I Atlas is representative of interstellar comets, do they all carry such unusual chemistry? And what does that imply about the protoplanetary disks that formed them? Dr. Loeb, for his part, remains unconvinced by purely natural explanations. The carbon monoxide hypothesis is interesting, he concedes, but it's ad hoc. We're inventing a special composition to fit the data rather than the data pointing clearly to a known process. When we see multiple anomalies, extreme eccentricity, strong non-gravitational acceleration, blue coloration, asymmetric coma, we should consider whether a single, unified explanation might be simpler than stacking multiple exotic natural processes on top of each other. This is the essence of the debate. How many anomalies can be explained by invoking increasingly exotic natural phenomena before the hypothesis becomes contrived? At what point does an artificial explanation, despite its extraordinary implications, become more parsimonious than a cascade of special pleading? Loeb's invocation of Occam's razor in favor of artificial origins is contentious precisely because it challenges the conventional hierarchy of explanations in astronomy. The scientific method traditionally favors natural over artificial, simple over complex, known processes over unknown. But Loeb argues that simplicity is not always the same as familiarity. An engine is, in some sense, a simpler explanation for sustained, directional acceleration than a finely tuned combination of exotic ices, asymmetric sublimation, and unusual spectral properties, provided one is willing to accept the prior plausibility of interstellar probes. And that prior plausibility is the crux. How likely is it that 3I Atlas is artificial? The answer depends on estimates of the prevalence of technological civilizations in the galaxy, the fraction that develop interstellar propulsion, and the probability that such probes would pass through the solar system in a time frame overlapping with human observation. These are the parameters of the Drake equation, notoriously uncertain, and subject to assumptions ranging from optimistic to pessimistic by many orders of magnitude. Surveys of exoplanets by the Kepler and TESS missions have revealed that planetary systems are common, with rocky planets and habitable zones numbering in the billions across the galaxy. But the leap from habitable planet to technological civilization is unknown. The Fermi paradox looms. If intelligent life is common, where is everybody? The silence of the cosmos, the absence of detectable signals or artifacts despite decades of SETI observations, suggests either that technological civilizations are rare, that they are common but short-lived, or that their activities are not easily detectable across interstellar distances. 3I Atlas could be evidence that resolves the paradox, not through radio signals or megastructures, but through physical artifacts passing through the solar system. If even a small fraction of civilizations launch interstellar probes, and if those probes are long-lived and numerous, the probability of detecting one increases with the volume of space surveyed and the sensitivity of detection methods. The discovery of Oumuamua, 2IY Borisov, and now 3I Atlas within a span of 8 years suggests that interstellar objects may be more common than previously thought, increasing the odds of encountering something anomalous. But the burden of proof remains high. Extraordinary claims require extraordinary evidence, and the evidence for 3I Atlas being artificial is, at present, circumstantial. The anomalies are real, the data are real, but alternative explanations, however exotic, have not been conclusively ruled out. Think about what that means for the immediate future of the investigation. Astronomers need more data, and they need it quickly. The most urgent observations involve high-resolution spectroscopy to identify the specific molecules responsible for the blue coloration, thermal infrared imaging to detect any anomalous heat sources, and continued astrometry to refine the non-gravitational acceleration and determine whether it remains constant or varies with distance from the Sun. There is also the question of radio communication. If 3I Atlas is artificial, it might be transmitting signals, either omnidirectional beacons or targeted communications. The Breakthrough Listen project, an initiative funded by billionaire Yuri Milner to search for signs of intelligent life, has the capability to scan interstellar objects for radio emissions. The project previously observed Oumuamua and found no signals, but 3I Atlas presents a new opportunity. Observations are reportedly planned for early 2026, assuming the object remains within range of the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia. The challenge is time. 3I Atlas is receding at approximately 30 kilometers per second relative to the Sun, accelerating as it escapes the Sun's gravitational pull. Each day that passes increases the distance, dims the object, and reduces the quality of observations. Spectroscopy requires collecting photons over extended exposures, and as the object fades, the exposure times grow prohibitively long. By mid-2026, 3I Atlas may be beyond practical observation by any current facility. This urgency lends the investigation a palpable tension. Scientists are aware that they may be watching a unique opportunity slip away, a chance to study an object unlike any other, whose properties could rewrite textbooks or confirm suspicions that humanity is not alone. The pressure is not merely academic, it is existential, a race against the darkness into which 3I Atlas is disappearing. Funding is another constraint. Observing time on major telescopes is allocated through competitive proposal processes, and directors must balance the demands of hundreds of research teams with diverse scientific priorities. Time allocated to 3I Atlas is time not spent on galaxies, exoplanets, or black holes. Some astronomers argue that the anomalies, while intriguing, do not justify disproportionate resources, especially when natural explanations remain viable. Others contend that the potential significance of 3I Atlas, particularly if it proves artificial, warrants exceptional measures. The debate reflects broader tensions within the astronomical community about how to prioritize discoveries that fall outside established research programs. SETI, despite decades of effort and significant public interest, has historically struggled for funding and institutional support. The study of interstellar objects is a nascent field, lacking the infrastructure and dedicated missions of more established areas. 3I Atlas is forcing the community to decide, in real time, how seriously to take the possibility of an artificial origin. Meanwhile, the data continue to arrive, each new observation adding complexity. In January 2025, the Keck Observatory captured a spectrum showing faint emission lines consistent with diatomic carbon, a molecule rarely detected in comets. The presence of C2 suggests carbon-rich chemistry, possibly consistent with Seligman's carbon monoxide hypothesis, but the lines are weak, and their interpretation is uncertain. In February, Hubble imaging revealed that the coma structure had changed, becoming more elongated and asymmetric, as if the outgassing were intensifying or shifting in orientation. The change correlates with the object's passage through perihelion, the point of closest approach to the Sun. But the timing and magnitude are not what models predicted. These incremental revelations keep the mystery alive but do not resolve it. Each piece of evidence is compatible with multiple interpretations, and the ambiguity is maddening for scientists trained to seek definitive answers. Dr. Karen Meach, an astronomer at the University of Hawaii, who led the early observations of Oumuamua, has been following 3I Atlas with a mix of fascination and frustration. We learned from Oumuamua that we need to act quickly and comprehensively when these objects appear, she remarked. But even with rapid response, we're limited by the faintness and speed of the targets. 3I Atlas is testing the limits of what we can do with current technology. Meach's team has been using the Canada-France-Hawaii telescope to monitor the object's brightness and color over time, hoping to detect patterns that might reveal the nature of the non-gravitational force. One pattern that has emerged is subtle but potentially significant. The non-gravitational acceleration does not appear to be symmetric with respect to perihelion. In a typical comet, outgassing peaks as the object approaches the Sun, reaches maximum intensity near perihelion, and then declines as the comet recedes. The acceleration follows this thermal curve predictably, but 3I Atlas shows acceleration that persists well after perihelion, declining more slowly than expected. The asymmetry suggests either a delayed thermal response, perhaps due to insulating layers of dust, or a mechanism that is not purely driven by solar heating. Delayed thermal response is known in comets. The sublimation of deep buried ices can lag behind surface heating, producing outgassing that continues after the object has moved away from the Sun. But the magnitude of the delay in 3I Atlas is larger than typical, requiring unusually thick insulating layers or unusually volatile ices at depth. It is another piece that fits awkwardly into the natural framework. Here's where the investigation stands as of late 2025. 3I Atlas is confirmed as an interstellar object with the most extreme orbit ever recorded. Its non-gravitational acceleration is real, but inadequately explained by visible cometary activity. Its blue coloration contradicts expectations for cold, dusty surfaces and may indicate ionized gas or an anomalous heat source. The coma structure is asymmetric and variable. The spectroscopic data are sparse and ambiguous. The object is fading, and time is running out. Stop and consider that this is not an abstract puzzle confined to academic journals. If 3I Atlas is natural, it represents a type of comet that does not exist in the solar system, formed under conditions and compositions that challenge current theories of planetary system formation. Understanding such objects is essential to grasping the diversity of materials and processes across the galaxy, the raw ingredients from which planets and, potentially, life emerge. Scientists refer to interstellar objects as the building blocks of other worlds, and they mean it literally. The ice and rock carried by 3I Atlas may have originated in a protoplanetary disk light years away, shaped by the unique environment of a star different from the Sun. If 3I Atlas is artificial, the implications are existential. The object would be physical proof that intelligent civilizations exist elsewhere, that they have developed the technology to travel between stars, and that their artifacts traverse the galaxy in sufficient numbers to be detectable. The discovery would not only confirm that humanity is not alone, but would provide a tangible target for further study, an artifact whose design, materials, and trajectory encode information about its creators. The prospect is both thrilling and unsettling. Thrilling because contact, even indirect contact through a derelict probe, would answer one of the deepest questions in human history. Unsettling because it would raise countless new questions. Who built it? When? Why? And are they still out there? What does the presence of such probes imply about the longevity and fate of technological civilizations? And what, if anything, should humanity do in response? These questions are not idle speculation. Organizations such as the SETI Institute and Breakthrough Initiatives have already begun developing protocols for responding to confirmed detection of extraterrestrial intelligence. The protocols emphasize scientific verification, international cooperation, and transparency. But the discovery of an artifact like 3I Atlas would strain those frameworks. Verification would be difficult, scientific consensus slow to form, public reaction unpredictable. Loeb has been advocating for a proactive approach. He proposes launching a fast spacecraft to intercept 3I Atlas before it escapes the solar system entirely, a mission that would require rapid development and deployment, but could, in principle, rendezvous with the object within a decade. The spacecraft would carry instruments capable of high-resolution imaging, spectroscopy, and even sample collection, providing definitive answers to the questions that telescopic observations cannot resolve. Such a mission would be technically challenging and expensive, likely costing billions of dollars. It would require international collaboration and political will on a scale rarely achieved. But Loeb argues that the potential payoff, confirming or refuting the artificial hypothesis, justifies the investment. We spend comparable sums on particle accelerators and space telescopes to answer fundamental questions about the universe, he says. Is the question of whether we are alone not equally fundamental? The mission concept is not entirely fanciful. Precedents exist. NASA's New Horizons mission, launched in 2006, traveled to Pluto and beyond, demonstrating the feasibility of fast interplanetary spacecraft. The European Space Agency's Rosetta mission successfully rendezvoused with a comet, deployed a lander, and returned detailed data on cometary composition and activity. A mission to 3I Atlas would combine elements of both, the speed of New Horizons and the close proximity science of Rosetta. But time is the enemy. 3I Atlas is already beyond the orbit of Mars and accelerating. A mission launched today would take years to reach the object, and with each passing month, the required velocity and mission duration increase. By 2030, interception may be impractical with current propulsion technology. If humanity is to send a probe to 3I Atlas, the decision must be made soon. The political and financial realities are daunting. Space agencies operate on multi-year planning cycles, with missions selected through rigorous review processes. A rapid response mission to an interstellar object would require bypassing normal procedures, securing emergency funding, and convincing skeptical decision-makers that the scientific return justifies the risk and cost. Advocates face the challenge of articulating the urgency without overstating the evidence, of making the case for action while acknowledging the profound uncertainties. Public interest could be a catalyst. The story of 3I Atlas has begun to percolate beyond specialized journals into mainstream media, driven in part by Loeb's provocative statements and in part by the intrinsic drama of a mysterious visitor from the stars. Social media amplifies the narrative, with hashtags and threads dissecting the anomalies and debating the implications. The public appetite for space exploration and the search for extraterrestrial life remains strong, and a mission to investigate 3I Atlas could capture imaginations in ways that more conventional missions do not. But public interest is a double-edged sword. Sensationalism can distort scientific discourse, leading to inflated expectations and premature conclusions. The alien spaceship framing, while attention-grabbing, risks trivializing the serious scientific work being done and polarizing the debate between believers and skeptics. Scientists must navigate the tension between communicating excitement and maintaining rigor, between engaging the public and avoiding hype. Now about the data that remain to be collected. The most critical measurements involve spectroscopy, with sufficient resolution and signal-to-noise ratio to identify the molecular species in the coma unambiguously. If carbon monoxide is indeed the dominant volatile, spectroscopy should reveal its characteristic emission lines at specific wavelengths. If ionized carbon monoxide is responsible for the blue color, the spectrum should show fluorescence features distinct from scattered sunlight. If an artificial light source is present, the spectrum might show a blackbody continuum inconsistent with reflected sunlight, or emission lines from elements not expected in natural comets. Thermal infrared observations are equally important. An object radiating at 290 Kelvin should emit a predictable infrared spectrum peaking around 10 microns. Any deviation, hotter regions, unusual brightness distributions, or temporal variations would indicate heat sources beyond passive solar heating. The James Webb Space Telescope, with its sensitivity in the mid-infrared, is ideally suited for such observations, and proposals have been submitted to allocate time for 3I Atlas. Results are expected by mid-2026, assuming the object remains bright enough. Radio observations by Breakthrough Listen will search for narrowband signals characteristic of artificial transmissions. Natural astronomical sources emit across broad frequency ranges, but engineered signals are typically concentrated at specific frequencies to maximize detectability. A narrowband signal from 3I Atlas, especially if it varied in a structured way, would be difficult to explain naturally. The absence of such signals would not disprove the artificial hypothesis. The object might be inactive, damaged, or not designed to transmit, but their presence would be transformative. Astrometric monitoring will continue for as long as the object is detectable, refining the trajectory and the non-gravitational acceleration. If the acceleration is due to outgassing, it should decrease as the object cools and moves farther from the Sun. If it remains constant or increases, alternative explanations gain credibility. The trajectory itself may also encode information. If 3I Atlas is artificial, its path might not be random, but directed toward a specific destination or aligned with the motion of nearby stars. Researchers have begun analyzing the trajectory to determine where 3I Atlas came from, tracing the orbit backward, accounting for the Sun's motion, and the gravitational influence of nearby stars, suggests the object originated from the direction of the constellation Perseus, but the uncertainties are large. Identifying a specific stellar system of origin is difficult, because 3I Atlas has been traveling for potentially millions of years, during which time both the object and its home star have moved significantly. Still, the trajectory provides clues. The object approached the solar system from above the ecliptic plane, the flattened disk in which the planets orbit, suggesting an origin well outside the galactic plane or from a system with an inclined orbit. This geometric detail is not trivial. Most natural interstellar objects are expected to approach the solar system from random directions with no preferred orientation. If future interstellar visitors show a statistical preference for certain directions, it might indicate a common origin, a nearby star-forming region, a disrupted planetary system, or even a network of artificial probes. The sample size is still too small to draw conclusions, but each new interstellar object adds to the dataset. Read between the lines of what astronomers are not saying publicly but discussing privately. The possibility that interstellar objects like 3I Atlas are not rare anomalies, but a common component of the galaxy, a population of wanderers that vastly outnumbers the bound objects in any single stellar system. If true, the interstellar medium is not empty, but filled with rogue planets, comets, asteroids, and perhaps artifacts drifting between the stars. The solar system, in this view, is not isolated but constantly permeated by visitors, most of which pass unnoticed because they are faint, fast, and fleeting. This paradigm shift is unfolding in real time, driven by improved detection capabilities and the serendipitous discoveries of objects like Oumuamua, 2I Borisov, and 3I Atlas. The Vera C. Rubin Observatory, scheduled to begin operations in 2025, will survey the sky with unprecedented depth and cadence, detecting transient and moving objects at rates orders of magnitude higher than current surveys. Estimates suggest Rubin could discover one interstellar object per year, possibly more, building a statistical sample large enough to characterize the population. If 3I Atlas represents a class of objects, carbon monoxide rich, highly active, spectrally anomalous, Rubin will find others. If 3I Atlas is unique, an outlier, or an artifact, that singularity will become apparent as the sample grows. Either outcome advances understanding, but the implications diverge sharply. The question is whether humanity will be prepared to respond. Detection is one thing, characterization is another, interception is yet a third. Each requires infrastructure, funding, and planning. The astronomical community is beginning to recognize that interstellar objects demand a new kind of observational strategy: rapid response, multi-wavelength coverage, international coordination. Ad hoc efforts, while successful so far, are not sustainable as the discovery rate increases. Proposals for a dedicated interstellar object observatory have been circulated. Such a facility would combine wide-field survey capabilities with rapid follow-up instrumentation, enabling detection and characterization within days of discovery. The observatory might include space-based components to overcome atmospheric limitations and achieve higher sensitivity. Cost estimates range from hundreds of millions to billions of dollars, sums that require national or international commitment. The scientific case is strong, but the competition for resources is fierce. Astronomy is in a golden age, with transformative missions targeting exoplanet atmospheres, black hole imaging, gravitational wave detection, and cosmic microwave background polarization. Every field makes compelling arguments for investment, and interstellar objects, despite their intrigue, must compete within this landscape. Loeb's advocacy has been both an asset and a liability. His high profile and willingness to embrace unconventional hypotheses draw attention and resources, but they also polarize the community. Some colleagues admire his boldness and public engagement. Others criticize what they see as speculation exceeding evidence. The debate is not merely scientific but sociological, reflecting differing views on the role of scientists as public intellectuals and the balance between caution and imagination. What cannot be disputed is that 3I Atlas has reignited questions that Oumuamua raised and that Borisov partially settled. Interstellar objects are not uniform. They span a range of properties, some familiar, others strange. The strange ones, those that defy easy categorization, are the most scientifically valuable precisely because they challenge assumptions and push the boundaries of theory. Here's the problem for those seeking closure. The data will remain ambiguous. Even with additional observations, even with James Webb spectra and breakthrough listen radio surveys, the evidence may not compel consensus. Natural explanations will evolve to accommodate new data, adding layers of complexity. Artificial explanations will remain plausible but unproven, lacking the definitive signatures, such as radio signals or manufactured materials, that would satisfy skeptics. The ambiguity is not a failure of science, but a reflection of the difficulty of studying objects at the limits of detection, whose origins and compositions lie outside the parameter space explored by solar system bodies. Ambiguity is uncomfortable, but it is honest. It is the space where the next generation of observations and theories will be forged. In the meantime, 3I Atlas continues its journey. By late 2025, it will have crossed the orbit of Jupiter, still accelerating outward. By 2027, it will pass the orbit of Saturn, dimming to a faint point of light detectable only by the largest telescopes. By 2030, it will approach the orbit of Uranus, and by 2035, Neptune. Sometime in the mid-2040s, it will cross the heliopause, the boundary where the solar wind gives way to the interstellar medium, and re-enter the void from which it came. The object will carry with it the mysteries it brought, unanswered questions encoded in its trajectory and composition. For humanity, 3I Atlas will remain a tantalizing enigma, a visitor whose true nature may never be fully known. The data will be archived analyzed and reanalyzed by future scientists with better tools and broader context. Perhaps decades hence, the discovery of similar objects or advances in theory will finally resolve the ambiguities. Or perhaps 3I Atlas will be confirmed as artificial, either through belated reanalysis of the data or through future encounters with similar objects that leave no room for doubt. If that happens, historians will look back on 2024 and 2025 as the moment when humanity first glimpsed evidence of intelligence beyond Earth, not through radio signals or megastructures, but through a small, fast-moving object that passed through the solar system and was almost overlooked. Think about what that means for the present moment. Scientists are working not only to understand 3I Atlas, but to ensure that, should the truth be extraordinary, the evidence is preserved and the opportunity is not squandered. The stakes are asymmetric. The cost of investigating and finding nothing unusual is measured in time and resources. The cost of not investigating and missing something extraordinary is immeasurable. This asymmetry drives the urgency. Even those skeptical of the artificial hypothesis recognize that the potential payoff of confirmation justifies serious, sustained effort. Even those convinced of a natural explanation acknowledge that the anomalies are real and demand explanation. The scientific process, at its best, navigates this tension, maintaining both rigor and openness, skepticism and curiosity. The story of 3I Atlas is still being written. The final chapter will not come from a single observation or a single paper, but from the accumulation of evidence over years, the convergence of multiple lines of inquiry, and perhaps the discovery of new interstellar objects that contextualize what 3I Atlas represents. What comes next is both planned and unpredictable. The planned observations, James Webb infrared imaging, breakthrough listen radio searches, continued astrometry, will proceed on the schedules of their respective institutions. The unpredictable element is whether 3I Atlas will cooperate, whether it will brighten unexpectedly, emit a signal, or simply fade into obscurity according to natural law. Scientists are also preparing for the next interstellar visitor. Lessons learned from Oumuamua, Borisov, and 3I Atlas are being incorporated into observational protocols and mission concepts. The Rubin Observatory will be online soon, its algorithms tuned to detect the faint streaks of fast-moving objects. Plans for rapid response networks are being developed, enabling telescopes around the world to coordinate observations within hours of a discovery. The infrastructure is improving, the methods are sharpening, and the community is learning. In a sense, 3I Atlas is a test case, a rehearsal for the future when interstellar objects are detected regularly, and the question is not whether to observe them, but how to prioritize and characterize them efficiently. But 3I Atlas is also unique, its anomalies setting it apart from what came before and what may come after. It is the object that has pushed the conversation furthest, forcing the scientific community to confront the possibility that not every interstellar visitor is a natural comet or asteroid, that the galaxy might be more complex and populated than models predict. The possibility is no longer fringe. It is being discussed in peer-reviewed journals, debated at conferences, and funded through competitive grants. The shift in discourse is significant, a sign that the field is maturing and that the questions posed by interstellar objects are being taken seriously. Still, caution prevails. The default assumption remains that natural explanations will ultimately suffice, that the universe, while strange, does not require invoking intelligence where physics will do. This is the conservative principle that has guided science successfully for centuries. But conservatism must be balanced against evidence, and the evidence from 3I Atlas is, at minimum, provocative. Read between the lines of the scientific literature, and a tension emerges, the desire to solve the puzzle and move on, versus the nagging suspicion that the puzzle is more profound than it appears. The tension is productive, driving research forward, but it is also exhausting as scientists grapple with incomplete data and conflicting interpretations. For the public, 3i Atlas has become a symbol, a focus for hopes and fears about contact with extraterrestrial intelligence. The object's trajectory through news cycles mirrors its trajectory through the solar system, a brief, intense appearance, followed by a slow fade. The challenge for science communicators is to sustain interest and convey the nuances without either inflating expectations or dismissing the anomalies as insignificant. The broader context is that humanity is, for the first time, actively searching for and studying objects from other stellar systems. This is not science fiction, but science fact, enabled by advances in telescope sensitivity and survey strategies. The implications extend beyond astronomy to philosophy, anthropology, and even theology, as the potential discovery of extraterrestrial intelligence forces reconsideration of long-held beliefs about humanity's uniqueness and purpose. 3i Atlas, whether natural or artificial, is part of this larger narrative. It is a data point, an anomaly, a mystery. It is also a reminder that the universe is vast, ancient, and filled with phenomena that challenge understanding. The object's passage through the solar system is a fleeting event on cosmic timescales, but it may be remembered as a turning point, the moment when humanity seriously entertained the possibility that it is not alone. Or it may be remembered as a false alarm, a natural object whose properties, once fully understood, fit comfortably within the bounds of known physics and chemistry. Either outcome is scientifically valuable. Either outcome teaches something about the universe. But the possibility that 3i Atlas is artificial remains, and it will remain until the evidence conclusively rules it out or confirms it. That possibility animates the investigation, lending urgency and significance to observations that might otherwise be routine. It transforms 3i Atlas from a curiosity into a potential watershed, a hinge upon which the future of humanity's understanding could swing. The final question, the one that will linger as 3i Atlas fades into the distance, is this. If the data are correct, if the acceleration is real, the blue color is real, the orbital eccentricity is real, how deep does this mystery go? Is it a singular anomaly, an outlier whose strangeness is a coincidence of composition and geometry? Or is it a signal, a clue pointing toward a larger truth about the galaxy and humanity's place within it? The answer will not come quickly. It may not come at all within this generation. But the question has been asked, the data have been collected, and the investigation continues. Somewhere beyond the orbit of Neptune, 3i Atlas is moving, accelerating into the darkness, carrying its secrets with it. Whether those secrets are ever revealed depends on the persistence of science, the advancement of technology, and perhaps a measure of luck. For now, the mystery endures, a reminder that the cosmos is not fully known, that surprises await, and that the search for understanding is ongoing. The story of 3i Atlas is not finished. It is only beginning.